Thank you. Good evening, everyone. It's a real pleasure to give a keynote tonight, and it's really interesting to follow such a thought-provoking talk by my near neighbour in West Yorkshire, Mark. And I don't actually have a favourite equation, but I will put one up that is solidly in my top five. So tonight I'm going to give you quite a personal talk. There we go. Personal talk about the problem of carrying out groundwater control in poor aquifers. And I'm going to have to explain to you why I think that's relevant. So I'm going to have to tell you about the problem, then tell you what I mean by a poor aquifer. And I'll talk about these challenges, and then I'm going to come up with some ground investigation strategies and some design strategies and some very brief concluding remarks. So I'm going to begin by asking this question: what is a difficult groundwater control problem? I'm asking it rhetorically, I don't expect an answer, but I take the view that most people will visualise something like this, which is essentially a problem with lots of pumps and lots of water. And so we're in high permeability strata. This image here over on the left-hand side is from the Middle East. You've got a flooded chamber here, lots of pumps, lots of pipework carrying water out of the excavation, a lot going on. This picture over here is an older one. It's actually from the Medway Tunnel at Chatham in Kent, and that's about 400 litres per second coming from the discharge tanks of pumping from the Chalk Aquifer on a big dewatering system there. And my view is that I don't think that's in general such a difficult problem. And I take the view that in high permeability conditions, provided you have an experienced design team and you have an appropriate ground investigation, that should be relatively straightforward. I grant you, it may be expensive, it may be logistically difficult, you've got lots of pump and lots of pipe work and so on. The regulation might be quite onerous because you're going to have a large flow rate and therefore a large zone of influence that might capture lots of receptors. But from an investigation and a design perspective, I think it should be fairly straightforward. The reason I think that is that the aquifer should be easy to identify from the water strikes or strata descriptions. The groundwater observations might be quite accurate because you're not worried about slow equilibration of water levels. The permeability testing methods should be a good match to the ground conditions. And finally, the dewatering wells should be quite hydraulically efficient, so you might not need many wells or sumps to actually pump that quantity of water. So, in my view, what I consider the more challenging problem is if you're working in lower permeability conditions. And the reason I think it's more challenging is it's the converse of the previous slide, that I think the aquifers might be more difficult to identify because water strikes and strata description might be less clear cut. The groundwater observations might not be that accurate because you've got to wait for the levels to equilibrate, and time is always precious. You might not get a good set of groundwater level readings. Some of the permeability testing methods are not a good match for the ground conditions in low permeability soils. And finally, a really key point is that the dewatering wells might be quite hydraulically inefficient, and you might end up with very low, even almost potentially zero well yields. So this is all about poor aquifers. So I need to come up with some sort of definition of what I mean by a poor aquifer. So let's start with a definition of aquifer and aquitard. And it's not exactly a random definition, but I didn't put a lot of thought into where I got the definition from. It's from a particular publication, and hopefully these definitions are not controversial. So aquifer, from the Latin aquifer, water, and fer, to bear or to carry, is a layer or layered sequence of rock or sediment comprising one or more geological formations that can store and transmit significant quantities of water under an ordinary hydraulic gradient. And conversely, aquitard at the lower end of the permeability range is a leaky confining bed that transmits water at a very slow rate to or from an adjacent aquifer. I would argue you might have your own pet definition of aquifer and aquitard, but that covers the main things. So let's think about it in the context of groundwater control. So in groundwater control terms, a permeable aquifer, I would say you would have a clear expectation that a pumped well system is going to be effective as part of a temporary works for an excavation, provided you have sufficient knowledge of the ground conditions, the regulatory regime, resources, and so on. So here we've got an example. It's from West Yorkshire, I'm afraid, and it's some glacial sands and gravels, and you can see there's a well point system around the outside, and so they're pumping probably quite a quantity of water. They've lowered the groundwater levels, and you've got a grinding material there. Pretty routine groundwater control. So if we look at the aquitard end of things, and I know the people from Mott's in the room, this is from the Boston Barrier, and what you're looking at here is the exposed glacial till, a dimicton with the white fragments of chalk particles in it, in the bottom of the cofferdam. So in an aquitard, you have a clear expectation that pumped well groundwater control will not be effective, primarily due to low well yields. But equally, you probably don't need groundwater control because the material's very low permeability and probably behave in an undrained manner. So my little hobby horse here that I'm going to be talking about is this zone on the boundary between aquifers and aquitards, where there is sufficient groundwater flow to cause you problems during construction, but where it can be difficult to design and operate pumped well systems. We all like numbers because we need numbers to go in our equations, so it's pretty difficult to put a hard set of numbers on this, but I'm prepared to say here that I'm talking about the permitted range of about 10 to the minus 5 down to 10 to the minus 7 metres per second, but there are many nuances. For example, it's much harder to drain a genuinely uniform low permeability material compared to a material that's got some sort of secondary fabric in it, be it fractures or fissures, or be it sort of silt parting and so on. If you go back to the work of Peter Rowe in his Rankin lecture, he talks about the effect of secondary permeability, partings and so on in glacial soils makes a big difference. So to give, obviously thus far there haven't been enough photographs of soil and rock, so we're going to try, everyone likes to look at soil and rock, so we're going to try and get some pictures up. So here we're looking at a scenario, what you're looking at here, it's a vertical face cut in a low permeability mudstone, but I don't know whether you can see that there are a series, and I've highlighted them there, a series of thin limestone beds in the face, and the mudstone is almost impermeable. But the problem here was that we have almost these what you might term microaquifers there that are water pathways and the zones of mobile pressure so that you get risk of basin sewage and so on. So again here we've got a low permeability material that isn't homogeneous and we have to deal with it as we come across it. So a few more pictures here. This is one of my favourites. Back when I was starting my career, we dealt a lot with a stratum called the Braccian beds in the southeast of England. They've changed all the names now. This is the Wittering Formation, which is a Paleogene deposit that sits on top of the London clay, and it's a very subtle mixture of silt, clay and sand. And when you look at the particle size distribution, it's really hard to know, is it an aquifer, is it an aquitard? In this particular shaft, you get both situations simultaneously. So it's about a 25 metre diameter shaft, and what we can see over here where they've been excavating, it's quite blocky, and when you excavate it, you get quite intact blocks of quite clay-bound material. But down here, there's some dewatering wells, not installed by me, to my design, I might add, where you've got water flowing up from some probably sub-horizontal sand layers a little bit further down, and water's flowing out. So here you've got this complex thing going on. And I've got another picture of this shaft later on that illustrates a different point. This is a picture from the Conway crossing in North Wales, and what you've got here is you've got a slope that's been cut in a very anisotropic glacial lake deposit, glacial lacustrine deposit. And obviously a glacial lake deposit is laid down in, logically speaking, a glacial lake where you get seasonal deposition. So during the thaw period, you get coarser particles being laid down. During the periods when there's less mobile water around, you get finer particles. So you get this layer cake effect of silt, sand, clay, and so on. And here you've got very limited amounts of horizontal seepage coming out of this slope, and they're eroding this slope away. These are some pictures of two split driven tubes, and normally, or in situ, the various laminations are essentially sub-horizontal or maybe cross-bedded. But here, these tubes have been driven, and you can see how these horizontal bedding planes, or, as it were, have been dramatically distorted and disturbed by the driving effect of these tubes. This was samples from a long time ago, so hopefully things have improved since then. Here we're looking at a picture in the bottom of a large excavation on the east coast of England, and what you're looking at here is the classic glacial till, a low permeability diamecton, fragments of chalk in it. But you see here there's a really sharp contact, and here there's about a metre thick layer of fine sand within the glacial till that we exposed when we excavated down. This is another view of it. And of course, this sand layer, which is water bearing, was in exactly the wrong position to help us with excavation, so it was in the right position to be very inconvenient. So we had to do some drainage measures there. But again, you see, this is something, is this an aquifer, is it an aquitard? How do we deal with it, how do we categorise it? This is a large rock face. It's vertical, soil nailed, and got sprayed concrete lining on it as well. And here, there's some drainage, but you can just see here, again, that there are some gently dipping limestone beds. And here, the mudstone is generally really low permeability. You can see they've got surface water ponding on the excavation here because the vertical permeability is really low because of the mudstone, but it has a significant horizontal permeability contained in these localised beds. This is a picture from the English Midlands. It's in the Kellerways Formation, another mudstone-dominated stratum, but it has these thin siltstone and sandstone beds in it. So this was an excavation where the siltstone and sandstone beds had to be depressurised. The well yields were really, really low. So in this case, the permeability was too low to be done with a system of pump deep wells with submersible pumps. So a system of ejector wells was installed around the outside and successfully depressurised it. So if we're talking about aquifer definitions, for those who work in England and Wales, we need to talk about the EA BGS definitions because you'll be aware that the Environment Agency and BGS have a system of principal aquifer, secondary aquifer and so on. It's worth noting that there's a different aquifer classification system in Scotland and a different one further in Northern Ireland. But these aquifer classifications can sometimes be slightly unhelpful. To pick the example of chalk. Chalk is clearly a principal aquifer. It's a very widely used for water supply. But in the weathered chalk, if you get grade DM chalk, which is matrix dominated, and I hesitate to say it's going to got David Norb in the audience, a chalk expert, but essentially, in hydrological terms, DM chalk is a poor aquifer. Permeability maybe 10 to the minus 7, something like that, but it's in what appears as principal aquifer on the map. Similarly, the Oxford Clay Formation, clearly unproductive strata, but there are limestone beds in it, and I've done passive dewatering projects in the Oxford Clay Formation to depressurise these limestone beds. So just consider the generic definitions with caution. It's all about your own scientific information and your conceptual model. In reality, most of the poor aquifers I'm going to talk about here today are classified as various grades of secondary aquifers in England and Wales. So now I want to talk about, having told you what poor aquifers are in my definition, why they're a problem. And we need to go back to the very fundamentals of what a pumped well system is. An essential pump well system involves creating a series of groundwater sinks where we pump water to lower the groundwater level or groundwater pressure locally at that point, and that creates a hydraulic gradient towards these wells. And then the overall process of groundwater control by pumping is that we have a series of these sinks or wells that collectively lower the groundwater level. And here we can see you've got our individual sink as you might draw in a textbook with the groundwater flowing towards it. But in the real world, we have something more like this, where we're trying to have an array of wells, in this case, around the excavation. Each one of them is its own local sink. You get flow towards each well, and then collectively they lower the groundwater levels and they let us carry our excavation in relatively dry and stable conditions. So here we have the equation. Like I say, I really can't cope with the pressure of having to pick a favourite equation, but this one's absolutely in the mix. It's Darcy's law. I am, Mark, a staunch advocate of the negative sign in Darcy's law. And it's deceptively simple. It's a 19th century equation from the 1860s, and it describes the flow of water in a porous medium, and it's fundamental to geotechnical engineering. It is actually an underpinning of Tesago's effective stress equation. And in this formula, we have the flow rate Q equal to the product of the permeability K, which is hydraulic conductivity, the hydraulic gradient I, and the area A. And the reason that you need a negative term, the reason that it's essential, is that the groundwater flows down the hydraulic gradient, i.e. from high head to low head. And the key thing is that we can express the hydraulic gradient as delta H over L, delta H being the head difference and L being the flow path. And we can then look at it like that. So essentially the hydraulic gradient can be represented in some simplified form by the slope of your groundwater level or your piezometric level. Some of this pointer might be taken up there. It's worth saying that sometimes you might hear, the flow's non-Darcian. Like, for example, if you get high hydraulic gradients in fractured rock, they say that the flow becomes non-Darcian. It's really important to realise that that doesn't mean that the relationship between hydraulic gradient and flow is broken down. You're still getting flow in response to hydraulic gradient. What it means is the relationship is no longer linear. So I might have to try and see if I have a spare pointer. There we go, I'll try that one. So at low hydraulic gradients, the relationship between flow rate and hydraulic gradient is linear, but as you get to high hydraulic gradients, the flow becomes turbulent, more energy is lost, and you get a non-linear relationship with flow. But the point being, in pretty much every geotechnical situation you're going to come across, you're getting flow in response to hydraulic gradients. So hydraulic gradients are really important. And if we ignore the area A and we say we get rid of the geometry, it means that the flow rate is controlled by two parameters and two parameters only, the permeability K and the hydraulic gradient. And that's where our poor aquifers start to be problematic, because the gradient, the aquifer permeability can vary by a huge amount. If we compare, say, 10 to the minus 5 down to 10 to the minus 7 meters per second, that's a factor of 100 reduction in permeability. And according to Darcy's law, the potential for flow rates reducing by a similar amount. So, okay, in that case then, let's just compensate by increasing the head difference to get the hydraulic gradient up. But logically, you can't. You have a finite dimension of wells, height of well. You can only increase delta H by so much. So that means then that we just can't increase we can't compensate by increasing delta H to get the flow rate up. So therefore, there's an upper boundary on the hydraulic gradient you can generate from a well in a low permeability, and therefore there's an upper boundary on the flow rate for a given geometry. And that's the heart of the problem of these low well yields in poor aquifers. But you can also express Darcy's law in terms of a velocity. And so at lower permeabilities, things happen much more slowly. The practical effects of this are that the zone of influence around a pumped well expands much more slowly. Because if you look at the situation there, when you start pumping, there's no zone of influence. And then as time goes on, the zone of influence gets bigger and bigger by expanding outwards. In low permeability soils, that can expand more and more slowly. And that means that typically a pumped well system in a low permeability soil will need to have very closely spaced wells, because you're not getting much lateral connection between them. And also, as I'll talk about in a minute, the problem is that when you do your ground investigation boreholes, because the inflow is very slow, it might be that the groundwater inflow is missed in your investigation boreholes. And also with monitoring wells, as I'll talk about later on, that you might need quite a long period of time for the water levels to equilibrate. I just want to divert off slightly and talk about electroosmotic flow. This wouldn't be one of my favourite equations, but it's very similar to Darcy's law, the form of definition there. And in low permeability soils, you can apply an electrical potential gradient, in other words, apply a voltage across the soil, and groundwater will migrate slowly in response to that electrical gradient. So why would you bother doing that? The reason you might think of doing that is below about 10 to the minus 7 meters per second, groundwater sometimes will move more rapidly in response to an electrical potential gradient than it will move in response to a hydraulic gradient. And that's because the electroosmotic permeability varies much less with particle size compared to the hydraulic conductivity permeability. And so that's really why electroosmosis becomes a theoretical consideration at low permeabilities, because we're accepting that we can't move the water very effectively by applying a hydraulic gradient. So a final point on the challenges about poor aquifers is that you need to be aware of the effect of close source of recharge. There are quite a few places in the UK where we have gravels, maybe river toast deposits or fluvial glacial gravels over a low permeability material. This is based on a project in Camberley. So this is the Camberley Sand Formation, and you have the river toast deposits over the top of it in the Thames Valley. And here we have dewatering wells installed in refined grain material. So the dewatering wells are going to have a low yield. But if the gravels are in direct hydraulic connection with the sand underneath it, you've got a shorter flow path, you've got a higher hydraulic gradient. So essentially there's more water available to this, this area here, but our wells are limited by the material they're installed in. And I've known a number of projects where systems where the actual dewatering wells have been installed in what I would call a poor aquifer have not been effective. And it's often turned out that there's been a nearby source of recharge that's not been effective, not been identified. And so the conceptual model is fundamental to this. For example, you can sometimes get in the Thames Valley where there's a weathered zone on the top of the underlying material there, probably from periglacial effects. And if there is a weathered zone where maybe the Camberley sand had weathered to a clay or something like that, you would then not get such a direct connection, and this system here would operate much more effectively than this system here. And again, the conceptual model will help you identify that. So now to move on to ground investigation strategies. And I want to talk about limitations with ground investigations. In my experience in these poor aquifers, it's not uncommon for investigations to poorly characterise strata that have their hydrological properties on the boundary between aquifers and aquitars. They might not accurately identify the hydrological nature. I'll talk about examples where boreholes have been described as dry when the material clearly wasn't dry, and the groundwater level data you get from monitoring wells might not be equilibrated because you've not waited long enough. This picture is from that same shaft I showed you earlier on. So it's in the Wittering Formation, and what's going on here is that we're in the bottom of the shaft, and this is an unsealed ground investigation borehole that's flowing in artesian way, and the sort of blue-grey plume is the sand being washed up from the deeper borehole. There's obviously a lot to talk about in this slide. We don't have all night. First of all, is a type of investigation borehole that hasn't been that's not been adequately sealed in your investigation. But the really key point is on this project, nearly every borehole reported it as being dry or groundwater not encountered. Down to considerable depth below this. But yet, I can tell you that groundwater is very much there, and we'll talk about why that might be the case in a moment. So in terms of ground investigation strategies, hopefully we're all on board with the value of depth studies. So you need a depth study to identify the potential for aquifers and aquithards. You also, as well as the geology, you need to have a good knowledge of what's proposed to be built, because we're practical people. We're trying to understand the interaction between the proposed construction and the ground. And then also you use that knowledge to plan an intrusive investigation. As part of that intrusive investigation, you need to review the non-quantitative indicators of relative permeability. I'll talk about in a minute. You need to make sure monitoring wells are installed and that you allow time for them to equilibrate. And finally, you need to have appropriate permeability testing. And I'll go through these in a little bit more detail. So I'm a big believer in that when you look at both the posh borehole logs at the end, but also sometimes at the field logs that come from the drilling crews, there could be a lot of information on there that sometimes we don't fully value. So these are what I've classified as non-quantitative indicators of relative permeability. Which are the more permeable bits, which are the less permeable bits. Water strikes obviously fundamental to it, and I'll talk about water strikes in a moment. But also there's the water level readings taken during drilling. I was always taught, certainly back in the day when it was mainly shallow and auger drilling, that the readings at the end of a day are almost certainly affected by the drilling effects, and you would give more weight to the water level readings the morning after when the bores potentially had time to equilibrate. But of course, in a poor aquifer with low permeability, you might not get full equilibration overnight. Obviously, information on the drilling fluid behaviour, any fluid loss, percentage return and so on, any voids that are reported, these are all useful secondary indicators of permeability. And finally, if you're lucky enough to have some borehole fluid geophysical logging, where you run a sonde down a fluid-filled borehole, changes in the temperature, changes in the conductivity and flow meter readings can be very useful. So I want to talk about water strike. So again, let's define a water strike. And a water strike, I think, is a sudden or a defined inflow of water recorded during drilling. And we know when you apply it to a conceptual model, it's often associated with a strata boundary or other feature, and it can provide valuable data. But the problem is in poor aquifers, the water strikes will be slow and the inflow rates will be low, which means the water strike data might not be as reliable as we'd like. Obviously, in rotary drilled boreholes, if you've got a water-based fluid flush, that might mask or even prevent, by having a balancing head, the water strikes. But obviously, percentage flush return is also relevant. But in light cable percussion drilling, what we used to call shell and auger drilling, I have worked on multiple projects where what must have happened is that the rate of inflow, say in a silty sand, is so slow that a driller drilling quickly to get his bonus and so on might not notice that there's been seepage and the borehole will be reported as dry and groundwater not counted. I generally take the view that most drilling crews are trying to do a good job. I think they're just, it's the fact that when you combine rapid rates of drilling with these local materials, it's quite easy to miss that seepage. And even when water strikes are recorded, the short, maybe 20-minute wait for equilibration isn't long enough in these soils, and the water level you get during the water strike is not enough, is not high enough. So again, this is what you're looking at. You've got an inflow here through a defined zone, and in a short period of time, it may be perfectly reasonable and factually correct in the field to record that as dry, but if you were to wait hours, maybe even days, you'd get a completely different picture. And people generally accept that monitoring wells give better readings than readings taken during drilling because we generally have the time to allow them to equilibrate and to overcome the effect of drilling. But the problem is that equilibration in these aquifers might not last might not occur very quickly. And the classic situation we sometimes get is the drilling contractor, has a certain period of field work on site. They will take readings while they're doing the field work, but once the drilling contractor leaves site, there might be no further monitoring. And it might be that the water levels haven't equilibrated during that time. So therefore, a few water level readings at the end of field work might not be enough. Obviously, the monitoring well design affects how quickly it equilibrates, and you can get monitoring well designs that require a smaller volume to equilibrate, but they tend to be more expensive, more complex, and that they might not be appropriate for every site. Here's just a little set of diagrams. So over here we have a large diameter dewatering well, maybe 150mm diameter, and in any monitoring well there needs to be a flow of water volume to register a change. And relatively speaking, you need quite a large flow of water here to register a change. If you need a large volume and the inflows are slow, you get a long time for equilibration. You can reduce the time for equilibration by having a smaller diameter open monitoring well, maybe 50mm, 25mm internal diameter, and a smaller diameter borehole to reduce the volume of the filter pack. But then if you really want a rapid response, you can have electronic vibrating wire sensors either installed in the sand cell, or increasingly now, I would install them in fully grouted holes routinely and so on. And obviously, as we go in this direction, we're getting smaller volumes for water equilibration, more rapid response times, but equally greater complexity and more cost. So when I was preparing this, I really wanted to show you some data of a piezometer equilibrating after it's installed. But almost by definition, that data hardly exists because we're not monitoring it. But I did find this data, and it's from a project I was working on where we were carrying out some dewatering in a poor aquifer, in bedrock of about 10 to the minus 6 to 10 to the minus 7 meters per second. And this monitoring well was actually a distant one on a third-party site that we were monitoring for background readings. And we didn't pay much attention to it for months and months. And when we looked at it, we thought, what on earth's going on here? And it turns out that the third-party site that owned the site took water quality samples every month or so, something like that. And each one of these is the sudden drop of them taking not a huge quantity of water out of the borehole, with a whale pump and purging. But you can see that it takes 1 to 2 weeks, in this case, for the water level to equilibrate to something like its original level. And this is something where we were actively dewatering in this stratum. It's not a tremendously low permeability stratum. So I found that very, very interesting. So in terms of permeability testing, I want to be very clear that I'm talking here about permeability testing in aquifers from 10 to minus 5 down to 10 to minus 7 and below. And I'm talking about routine testing. I'm not talking about nuclear industry testing where obviously they have to deal with much lower permeability and have high quality testing. Here I'm talking about routine stuff. And I'm broadly talking about in situ tests in boreholes. I'm not going to talk much about indirect methods like particle size distribution or borehole geophysics. And so we're talking here about a variable head test, rising and falling head tests in boreholes and monitoring wells, packer injection tests in boreholes, and well pumping tests. And if you think about the commonality across these tests, they all involve moving water in some way to create a hydraulic change to get a response, and then we analyse the response to get a permeability. So we're back to the same problem of Darcy's law, that if things are moving slowly, it can be hard to do these tests. So I'm going to go through a series of potential problems with doing permeability testing in these poor aquifers. The first one is pretty obvious and is common across all types of aquifer, and it's disturbance. And so we've drilled a hole to create a test zone, and in some way, and there are myriad ways we can do that, we've disturbed the ground. Generally, we've probably reduced the permeability. Occasionally, you might increase the permeability. And so here, if we do a test, are we actually measuring a reasonable permeability of the ground, or are we essentially measuring the permeability of this disturbed zone? And I know you can analyse it for a skin effect and so on, but the point being, we don't know much about it. One I come across more and more is where the initial groundwater level in the test doesn't match up with the conceptual model. The classic scenario would be that you're doing maybe a packer test or something during a borehole, and the initial water level recorded in the packer test has either been affected by the previous test or has been affected by the drilling. And therefore, the water level you record in a test is obviously your initial water level against which you analyse the response. And you do need to match your ground level, initial ground level, to make sure it's consistent with your conceptual model. This is like a practical issue that because the flow rates are so low, It can be difficult to pump in or out at the low flow rates, difficult to control the flow rates, difficult to measure the flow rates, and that's where the nuclear repository industry has sort of moved ahead of routine equipment. And finally, uncertainty in analysis. You know, there's loads of software around to look at it, but we need to go back to the fundamentals. We don't talk enough, I don't think, that most of the permeability tests we do don't directly calculate permeability or hydraulic conductivity. They calculate essentially a transmissivity of your test response zone. If you've got a response zone of length L, essentially most of the mathematical equations will give you the transmissivity, and then we work out, without realising it perhaps, our average K for the response zone. But what if our response zone isn't uniform? So here we've got a response zone where we have a low permeability bedrock, a bit like some of the ones I showed with the dipping limestone beds, low permeability K1 and a high permeability K2. The K average that you get from that test will be neither K1 nor K2. And obviously this is where having good borehole information, looking at the core, maybe doing optical televiewers if you can, borehole geophysics. But again, that's not always possible. But as a main point, you need to understand that you calculate transmissivity and get a K average, which isn't always appropriate. So I've spent the last 10 minutes telling you how horrible and difficult it is to assess permeability. Don't misunderstand me. I'm not saying stop doing it. We absolutely need to do it. But you do need to think about critically how you're doing it and then think about the data. And I want to now talk about going from test result to design values of permeability. And it's really important to validate your test results against the conceptual ground model and the visual description of the strata, including particle size trends. A really key point is you need to be prepared to exclude high and low outliers that conflict with your model, and also to exclude any test that you identify as bad practice. It's absolutely fundamental, because if you get a test that's really badly clogged, it could be 100 times lower than the in-situ permeability, and that's massively going to skew any analysis you do. As a result, I'm not a fan of particularly sophisticated statistical analyses due to the wide range of possible test results. I can probably hang my hat on doing like a geometric mean after you take the outliers away. And therefore, those of you, anyone who ever works with me or sees my reports, I always insist that we never quote a single value of permeability. We would normally quote a range of permeability values, and you very much limit the number of decimal places to avoid giving a false sense of precision. Because it's all about communication. We shouldn't communicate too much precision. But you also need to remember that particularly if you're writing this report for someone who's less geologically minded, they're going to look straight at the higher end of the permeability. So if you say the permeability is from 5 × 10⁻⁶ to 5 × 10⁻⁷ meter per second, the higher end will give you a higher range, higher flow rate, and everyone will worry about that. I'm not worrying about that. I'm worrying about the 5 × 10⁻⁶ value, and that's the whole point of what I'm talking to you about tonight. So now in terms of design strategies, what are the common elements of design strategy in these conditions? It goes without saying, so I'm going to say it, conceptual model. Everything comes back to conceptual model, which is going to evolve as you get more data. The vast majority of big problems I come across aren't about numbers, they're about the concepts. For groundwater levels, think holistically and use all information. Have a conceptual model. Look at these non-quantitative indicators, water strikes during drilling. Try and get water level data from monitoring wells, but again, be aware that it might take weeks in some cases for open wells to equilibrate. I've got a case history here that I was involved in a review capacity. And so it's a structure somewhere in the UK in a local mudstone, and the groundwater from boreholes, without exception, reported the logs as dry. No surprise there, we're in mudstone. And it pains me to say, but the designers, not a company I personally work for, assumed that the ground level was below the base of the structure, and furthermore, they designed for 0 pore pressures. Luckily, before construction started significantly, someone reviewed it, and they discovered that the ground level was actually close to ground level, and the structure had to be significantly redesigned at quite a lot of inconvenience. And my argument is a conceptual model would have avoided that, because in the UK it rains quite a bit, and quite a bit of that water infiltrates to the ground. And if you have a low permeability stratum near the surface, you tend to find that there is a shallow water table. And I think what would have happened in this case is that the boreholes have been drilled and no groundwater has been observed because of low permeability. And so in this case, if they were to excavate this cutting, Obviously, you get an undrained effect when you loaded it. You get suctions initially, and then over time, a pore water regime would set up with positive pore pressures here. So it had to be designed. And of course, even if this, let's say there was some aquifer that was underdrained in this clay layer, and it does happen, even if there was an underdrainage effect, you would not get zero pore water pressures. The classic example of this is the London Basin, where most of you will know that we have the Aquifers, the London Clay Formation, and the clays in the Lambeth Group. And the chalk aquifer beneath the clays has been depressurised over many decades. And so there's a vertical downward height gradients occurring in much of the aquitard. But of course, the pore water pressures are not zero in this underdrained clay. They're just less than hydrostatic. So that product I've described is an absolute failure of the conceptual model. So we are here talking about trying to control groundwater, so we need to use groundwater control methods. And in these poor aquifers, we need to select the right method. And we need to get methods that are a good match for the well yield and a good match for the low lateral connectivity between wells. The well response zones must be targeted to the most permeable zones if present. And it's worth saying, I quite like passive methods sometimes where you're not pumping directly, letting the water overflow. That can be good. Many of you will be familiar with this diagram, which comes from Surrey Report C750, that relates drawdown on a vertical scale to permeability here with different methods. This work was actually based on work by Toby Roberts in the 80s and 90s, and Toby has recently led some work that has actually updated that diagram. It was published in the IC Proceedings, and it'll be in the new Geological Society Working Group book. And if you notice, the main change on this is that we've now got a section on vacuum deep wells and eject wells and well points working in these poor aquifer zones. This is the poor aquifer zone here, this zone here. And so one of the points here is where these methods apply a vacuum to the well. So I'm going to talk briefly about vacuum wells. So the definition of a vacuum well is where the void inside a well, we essentially create a partial vacuum below atmospheric pressure. And this approach works by increasing the applied head reduction, the delta H in the well, so therefore we can increase the hydraulic gradient, and therefore that could potentially increase the inflow and increase the yield. This diagram here shows what often happens in a conventional well. The well's open here, so the inside of the well is at atmospheric pressure, and we're pumping water only. We've got a big drawdown inside the well. Because of our well losses for various reasons, we only get a relatively modest drawdown outside the well. If we are able to seal the top of the well and pump both air and water for approximately the same water level in the well, some of the vacuum is used to overcome the well losses, and we get a greater drawdown in the aquifer outside if it works effectively. Ejector wells are a really good method to do this because if you seal the top of the well, they generate a vacuum automatically, but you can modify deep wells to apply vacuum, and you can also try and manipulate well point systems to generate a vacuum. I've got some data here, and there's a lot going on, so I'll try and take you through it. It's from a pumping test in London, a 7-day pumping test for a single test well in the intermediate aquifer below London. The groundwater levels were really highly tidal. This is the data after tidal correction, because the tidal response was so huge. So we've still got a lot of noise in there. But again, you can see the drawdown response. It's not mass tidal effect. We had 7 days test duration, and the first 3 days of pumping, there was no vacuum, and the well pumped 0.3 litres per second, quite a low yield. And for the next 4 days, a vacuum was applied, and we got nearly twice the flow. So here we have the blue lines of the flow rate on this scale here. When we started the pump, it takes a while to adjust the valves and so on, so that the flow rate went crazy all the way up to 5 litres a second for a few seconds, went down, and then we stabilised at this 0.3 litres a second, and then you clear the very clear step increase in flow rate when vacuum was applied. What's interesting is you can see this is initial drawdown when we start pumping, but in some cases we're getting almost the same magnitude of drawdown applying the vacuum. And what's interesting further, some of these wells are more than 150 metres from the pumped well. So the vacuum effect in this case isn't just being used to overcome the well losses, it's actually increasing a greater drawdown aquifer and therefore a greater hydraulic gradient. It's true, I have done vacuum on other projects where the vacuum has been tremendously ineffective, probably because I think the wells were clogged up. But here they got a good well design and the vacuum was quite effective. Just final couple of slides now, how to deal with close sources of recharge. I've mentioned how that if you have a close source of recharge, a separate aquifer in hydraulic connection with the poor aquifer, then that can overwhelm your wells in the poor aquifer. And so sometimes you need to have a separate dewatering system in the poor aquifer to reduce the head. This is an example from the A55 Conway Crossing project where there was a large bund, and the poor aquifer in this case was the glacial lacustrine deposit with a horizontal permeability, we back analysed this, of about 4×10⁻⁷ metres per second. There's some glacial till above it, which was genuinely low permeability, and then there's some alluvial sand and hydraulic till above it. And in this case, actually, there's a separate dewatering system in the alluvial sand, but in this particular slide, it's not to reduce the recharge to the poor aquifer. It's because this glacial till is acting as a definite separating layer. It's just the fact that we needed, a separate dewatering system because of the separating layer. But subsequently, there was a large blow or uncontrolled inflow in this excavation, and the inflow occurred, and we ended up with about 250 litres per second of water coming in one particular location. Very problematic. And obviously, if you do the maths, if this is genuinely a poor aquifer here, there's no way it can generate that sort of inflow. In reality, the ejector system from the poor aquifer was pumping about 10 litres per second, a tiny fraction of the flow there. So the conceptual model kicked in with investigations, and some of the investigations found that there was a significant channel of glacial fluvial gravels. And again, if I had, a pint of beer for every time a buried glacial channel has caused a problem, I'd have quite a few pints of beer. But it's a very real problem. My talk next week on the Kilsby tunnel is about a glacial channel in the 1830s that caused big problems. And once you know it's there, once you've picked it up and you've got your model, then you have to directly dewater it. And there were a small number of very high capacity wells installed here, and they depressurised it and dealt with it in that way. So my hypothesis tonight, and it's a very personal view, is that I'm not worried about high permeability conditions. Can deal with that. What worries me is the poor aquifers that are at the boundary between clearly water-bearing aquifers and almost impermeable aquitards. Groundwater flow is governed by one of my top 5 equations, Darcy's law. And when you look at that, including the minus sign, you can't compensate for the low permeability by increasing the hydraulic gradient. And therefore, low well yields are an absolute outcome of that. This also creates challenges for ground investigations, including identifying aquifer zones, representing groundwater levels, and being aware that good drilling crews may well report these poor aquifers as being dry, and you need to factor that information into the mixing conceptual model. And it comes back to it, I'm sure we're going to hear the phrase conceptual model a lot over the next few days. A robust conceptual model and understanding the factors affecting groundwater flow, it's possible to navigate through these problems, and I hope you've enjoyed my presentation tonight. Thank you very much.